Okay, so I'm hoping that the recording is starting. You guys might not be able to see the video very clearly. There is a little too much light in this room, but nonetheless, we are going to get started. So, welcome. We are going to be going over the first several chapters in our biology course, and this is for the Campbell Biology 12th edition. So, let's just get started. Now, we are in the second semester of your general biology, and this is a semester where we're going to be heavily focused on molecular interaction within the cell itself. So these first couple chapters that we're going to be going over is mainly understanding the molecules and atoms involved in it, as well as the behavior of these atoms chemically wise. Why is it that they work, and how it connects with the overview of biology. Now, hmm, with this, as chemistry was a prerequisite course, I will be going through these somewhat faster than if you never had these courses before. But since general chem was a prereq, we are going to get through this. And I'm not going to go over too much in terms of what is a proton versus what is an electron. More so, what I want you guys to understand is the location. Where are the protons, neutrons found, as well as the electrons, and what electron is involved when forming chemical reactions, and what electrons are involved when, we have a polar moment, for instance, like where are the electrons, what orbitals, etc. So those are generally background knowledge, but it is going to be an application here. So understand the difference between an atom and a compound. Compounds are just multiple atoms bound together into a molecule, multiple different atoms. An element can be a big molecule, but it's not going to be considered a compound just because compounds um, generally contains different types of atoms. Now, the number of protons and neutrons is what determines the element itself. Protons mainly for the element, and neutrons is what affects the isotopes for that. And then the electrical charges or the electrons will determine what type of ion this element would represent. Okay. So just know organisms are composed of matter. We are made up of elements. We're made of carbon, oxygen, nitrogen, hydrogen, sulfur, phosphorus, for the most part. Now, there are some trace elements that we are made up of, but just let's go through the background just a little bit. Elements, again, are a substance that cannot be broken down anymore. If it's a carbon element, if you break it down, you have more carbon elements. I mean, there's nothing that we can distinguish in terms of one chunk from another. That is, in essence, the definition of an element. A compound, again, is more than one element combined together. And when we break them apart, then we can have one chunk having oxygen and the other chunk having carbon. So that is what constitutes for a compound. Okay. Now, there are going to be essential elements that are required for life. And in our textbook, we labeled them as the 92 natural elements. So, roughly around 20-25% of the total elements on your periodic table. Now, out of the 92 natural elements, only about four or five of them make up around 95 to 96%. And the remaining 4% generally will consist of something between calcium, phosphorus, sulfur, potassium, etc. The main big minerals that you guys are well aware of for your health. I mean, this is why we tell you guys drink a lot of milk, take calcium supplements, potassium supplements, etc., because they're generally going to be in a larger percentage. Now, for all the other elements, all the other minerals, such as magnesium, such as iron. Those are what we constitute them as trace elements. They don't really consist of big amount inside the human body, or in essence, life itself, but they are required every so often for the orientation or the shaping of the different proteins and molecules, organic molecules found within our body and cells body. So, if you want a nice breakdown of what it is, here's a nice chart highly encourage just looking through it. And we can see around 96, 97% is the main four: oxygen, carbon, hydrogen, and nitrogen. Okay. Now, atom is the smallest unit of matter. Write this down. Atom is the smallest unit of matter. Do not get this confused because we are going to be talking about cells a lot and in the future chapters. The atom is what builds up matter, whatever we are made up of. However, cells are the smallest unit of life. They are the first living piece uh, that builds up all of life. Okay. A lot of my students usually get confused between the two. They kind of think that they're all together. So just write it down if you have to. Atom, smallest unit of matter, cells, smallest unit of life. Okay. Neutrons, protons, electrons. Again, you guys should already know this by this point, but protons, neutrons are found within the nucleus of the atom in the center. Now get familiar with the term nucleus because the location-wise is going to be very similar to that in biology when we start discussing the components of the cell. And the electrons are found around it. Now, in atomic number, mass number, and atomic mass, please go ahead and review this. There's a lot of practice questions online, but if we give you something like 14-C, right? And let me write this with my pen. Now, this is going to be very wonky on this because we are using an older PowerPoint. So you might see a little bit of scratches on the screen itself. But if I give you something like this, where, let me see where the pen is now, 14, okay, dash C, right? Or I give you something like C with the 14 on the top and then like 12 on the bottom. Like you would need to be able to decipher what this means, where 14 is your mass number, it's on the top. And the bottom left-hand side, it shouldn't be 12. Again, carbon is not 12. Atomic number 12, it's atomic number 8, I believe. So the atomic number is incorrect, but I can't see my pen right now because I am using an older version of PowerPoint. So scratch out the carbon 14 example right here, this one. Okay. Oh my gosh. Let me redo this because this is just really bad. So let's go back. I hope I can see my pen here. Screen. Uh Pointer option. Laser pointer. Okay, so I have my mouse here. And then we're gonna do a pen. And it doesn't show me the pen. So 14, okay, with the carbon, big carbon, and then lowercase 8 or 6 or something. So for this example, I don't recall the periodic table off the top of my head. 14 will represent your mass number. Okay. And you know what? Let me see if I can just write it. Mass. There we go. Mass number. And number 6 right here would represent the atomic number. Okay. Now, with this example, atomic number will always represent the number of protons. Okay. In regards to your mass number, this is always going to be equivalent to your protons plus your neutrons. And depending on if it's a neutral charge right here, a -1 or +1 will determine how many electrons there are from neutral point. Now remember, number of protons and number of electrons are always equal when there is no charge. But if you have a -1, you're going to add 1 electron because now it's more negative. If you have a +1, you're going to remove an electron. Okay? So hoping that makes sense. Again, let me know if it is, oops, if it doesn't make sense, and then we'll go from there. Okay? All right. Let me get the zoom out again because we got to share the screen again. All right. So now, hopefully that makes sense. Now, for atomic mass, we generally in chemistry talk about it in regards to grams per mole. Now, this is great, but just note that as we're starting to talk about mass in general in biology, we're going to use Daltons instead. Kilodaltons to represent the mass of an organic molecule. So I just want you guys to know that because we are going to be switching it up from a general chemistry perspective. Now, isotopes, again, are same elements, meaning they have the same number of protons, The only thing that's changing from one or the other is the number of neutrons found within the element itself. So if you have uh, carbon 12 versus carbon 14, the only change between carbon 12 and 14 is the amount of neutrons found inside the nucleus, where carbon 12 has 6 neutrons and carbon 14 has 8 neutrons. The reason being is because carbon has the value, atomic number of 6. Again, I don't recall the periodic table. Let me see. Is it 6 or 8? You know what? I have a chemistry book here. Let me just tell you guys what it is. We have a chemistry book right here, and it should be periodic table is right here. Carbon is atomic number 6. All right, cool. So I was right. Okay. So that is what an isotope is. Now, radioactive isotope is radioactive because the instability of the amount of neutrons within the nucleus makes the whole uh, particle unstable. It'll start to randomly degrade spontaneously. This is what we call a radioactive decay. And it's just going to start losing its isotopes or its extra neutrons, okay? Or split the atom into two smaller atoms, okay? Or two smaller particles. Now, molecules again, are multiple atoms bounded together, but with the binding, you can have different types of bonds. Now you have single bonds, double bonds, triple bonds. Just know that these are covalent bonds where the electrons are being shared from one atom to the other. More specifically, it's the valence electrons, okay, the outermost electrons on the atom. If you need a review on this, I recommend watching some YouTube tutorials on structures of atom, basic chemistry, chemistry 101, just to give you guys a bit of a visualization. Now, there might be some practice problem on the online resource for Pearson. I highly encourage you going through their material if this is still slightly confusing for you. Okay. And with the binding of these electrons, we have electronegativity. Now, electronegativity, you guys heard this to death, oxygen, oxygen, oxygen. Whenever you see the oxygen atom, a nitrogen atom, a phosphorus atom, or something that is close to the top right-hand corner of your periodic table, don't forget your periodic trends, anything that's close to the atom fluorine, F, the letter F, is going to be more electronegative. The reason being is because we have a lot of protons inside the nucleus of that atom. And that protons is highly attracted to the negative charge of the electrons. So as you get closer to fluorine, aka or oxygen, you're going to have a very strong attraction to electrons. And because of this, if you bind that atom, that electronegative atom, to another atom, remember, atoms are made out of electrons on the outside, that electronegative component of oxygen is going to start pulling electrons away from the other atoms, giving a polar covalent behavior. Okay, let's rewind. Polar covalent. When you have two atoms bounded together, one's oxygen, for instance, and the other one's carbon, oxygen atom is going to pull electrons away from the carbon. Because of that, you have a polar moment. Now, why are we using the term polar? Reason being is because like North Pole, South Pole, positive pole, negative pole, when the electrons are moving towards the electronegative atom, it becomes more negative. Okay? More negative. Now here, I'm going to do my pen again. So say that I have oxygen, and then I have carbon right here. Now, because oxygen is bound to carbon, what's going to happen? I pull electrons towards oxygen, making this side more partially negative, leaving carbon to be more partially positive. Note we have a negative N and a positive N. Because of this, this represents a polar covalent behavior or a dipole moment. Now, if there is no pole or if there's equal pole of electrons in opposite, equal and opposite direction, then we have non-polar covalent bond because there is no side that's positive and negative. It's just one or the other. It's either all equally dispersed. It's just equally dispersed. Okay. So right here is an example of a water molecule. Now, water is that universal solvent, which we'll talk about in the next chapter in this PowerPoint. Just know Notice where the electrons being pulled. All the electrons are being pulled towards the oxygen here. And because of that, we have a partially negative behavior towards the oxygen. And on the other end, we have hydrogens that are partially positive. These intramolecular forces, intra, not inter, intra means within the same molecule, intramolecular force is what we call a polar covalent bonding. Okay. Now, if we divide the molecule in half from top to bottom, we have the negative side and the positive side, making this molecule polar. Okay. So ions, charges, you guys know this. Positive charge, negative charge. Sodium, positive one. Chlorine, negative one. Sodium, being the positive charge, is the cation ion, and chlorine, being the negative charge, is the anion. And together, they form a ionic characteristic or an electrostatic characteristic. Now, this is a giving of electron. That means one atom is freely giving to the electron to the other atom. Reason being is because they want to become a noble gas. They want to have stability in their shells. So if they have extra electrons to give away, they're going to freely give it away. So we see right here that the valence of sodium, which is one electron, and the valence of chlorine, which is 7 electrons, sodium just needs to give away one electron to become a complete octet on the outside, right? It gets rid of its outermost shell, strips away that electron, gives it to chlorine, and now sodium becomes a full octet on the outside, very, very stable, like a noble gas. Chlorine, now receiving the extra electron, fills up their outer edges as well, completing the octet rule, and has a noble gas characteristic. Hence why this is an ionic characteristic. But when we are dealing with ions, when we're dealing with ionic compounds, this is what we call electrolytes. Now, your Gatorade, your Powerade, your IV fluid, right, are all containing electrolytes. This is why when you drink them, they are salty tasting because of this. Now, salts is just our way of saying electrolytes, or our way of saying ionic compounds. Salts. Okay. So, most of the strongest bond is a covalent bond. Okay. Even in the presence of a universal solvent like water, covalent bond stays put. Ionic bond being the second strongest without water being present. Okay. Now, once water gets involved with an ionic bond, it becomes one of the weakest and it starts breaking apart. This is why when we dissolve table salt into water, it forms an electrolyte solution or an aqueous solution. Now, don't get this confused with sugar molecules, okay? Because sugar molecules are polar molecules that can also dissolve in water, but does not form an ionic characteristic unless there's ionic components attached to it. Okay, so just be careful with that. Hydrogen bond. Now we're going to start talking about the weak intermolecular forces. Intermolecular force, meaning that they are going to interact with one molecule to another molecule, not within the same molecule. Okay. So hydrogen bonding is very, very specific. It is probably one of the most important intermolecular force that we are going to be discussing in biology. It involves a hydrogen. Now, hydrogen bonding does not always have O bounded to H. It doesn't need to have oxygen. You can have nitrogen bounded to H. This will give a hydrogen bond. You can have sulfur bounded to H, maybe, but definitely nitrogen bounded to H. Okay. Other atoms can replace oxygen for this hydrogen bonding behavior. Okay. But the main crux of what hydrogen bond does is that if we have a positive and a negative N on a molecule, and we have another positive and negative N on another molecule, then the positive N on one molecule can attract the negative N on the other molecule. Meaning, right here, we have water molecule, and then we have ammonia. The positive part of hydrogen on water, due to its polar covalent tendency, intramolecular force, causes hydrogen to be partially positive. There's a lone pair on ammonia, right? NH3, you guys had this as a lab for those who are taking it, who have taken it last year in general chemistry. We asked you guys to draw the Lewis structure of ammonia. Ammonia has a big lone pair on top, which is negative. This positive end is going to get attracted to this negative end, and it will stick. Now, the best way I can describe hydrogen bonding for you guys is treat it like a magnet, right? You have a fridge magnet, you put it against something that is attracted to the magnet, and what happens? It gets attracted and it sticks. Now, question, can we pull the magnet off? Is it covalently bound? Is it permanently bounded to the fridge? You have a fridge magnet, you bind it to the fridge. Is it permanently bounded? No. You can still pull it off, right? Because it is a weak attraction, a weak intermolecular attraction. Now, keep this in mind. Many weak intermolecular attractions can become extremely strong. Think of Velcro. Think of 1,000 fridge magnets. You stick it to the wall. Can you pull it off? No, because there's so many weak interaction that accumulates and becomes very strong. Okay? But individually, it's very weak. So these accumulations, these interactions is what we call van der Waals. I'm totally mispronouncing. It's a German, I think it's German. Van der Waals attraction. And it's just attraction between molecules that are similar to each other. Okay. So think of a gecko's foot. Now, for us, as human beings, we don't have the ability to climb up walls by just sticking to it. We're not Spider-Man, right? We can't just stick to a wall and just climb up. Geckos have a very unique, how do I put it? Development, adaptation, right? On their feet that has these tiny, tiny, tiny little suction cups. And we can see it right here in the image below. There's these tiny little suction cups that binds, okay, with weak interactions that will stick to surfaces and will give the gecko the ability to climb up the wall. Now, there's a lot of things that aid in that ability. One, the gecko is very lightweight. It's not overly heavy. Two, it can overcome the force that the gecko produces, can overcome the gravitational pull. So that's okay. But overall, just know is that these multiple, multiple tiny little suctions, you can think of them as little suctions right there, accumulate enough so that it can walk on walls, which is amazing. Okay. Now, molecules, they are going to be mimicking each other quite often. And the reason why is because of specificity. That's a little confusing. Let me explain. In our bodies, we have a lot of tools. These tools are what we call enzymes. Okay, get familiar with it. We're going to talk about it in chapters like 8 or 7, something like that. Enzymes are tools for the body. Now, just like with any tool, you need to have the correct use or correct thing that interacts with it. You're not going to use, what do you call? Let me think of a tool. A screwdriver, right? A screwdriver is a tool that we all know. You're not going to use glue with a screwdriver. You're just not. The glue is a different tool, right? It's a different thing that interacts with it. Screwdriver needs screws, right? It's very specific for what it needs to do. So in our bodies, we don't have physical tools. We have organic tools like molecules, hormones, other substrates. And they will perfectly fit as best as they can into an enzyme's active site. Okay, the activity site. So for a hammer, the activity site is the face of the hammer. For a screwdriver, it's the Phillips point, right? That's the active site of that tool. For an enzyme, such as a receptor, the active site is found right here, where I'm circling, right? That's where the molecule is going to bind to it. Now, you don't need to have exact binding. but you need to have it very darn close, like 98% close enough so that it fits near perfectly. And then from there, it will send a message to the rest of the cell. So endorphins and morphine, you can see that the active site or the active component of the molecule is a near identical, with the exception that you have one more oxygen atom right here. But everything else is cyclical. Okay. So chemical reactions, you guys know, if I wrote A plus B yields C, you'll see that A plus B is your reactant side. It's left of the yield symbol, which is this. This is your yield symbol. Okay. And then C is your product. Now, for biology, instead of saying reactants, we also say the term substrates. So substrates is also interchangeable, but mainly we do this for enzymatic talk. Okay? So right here's an example, photosynthetic equation that we will eventually come across later in the chapter when we're talking about photosynthesis and cellular respiration. But the idea is identify what the reactants and the products are. So take a moment, look at it. If you said that this is my reactants and this is my products, you're correct. Okay. Now, equilibrium, okay, is not, and I really, really repeat this, is not I can go one way or the other way, right? When we write A plus B equalizes with C plus D, it's not like, oh, there's a forward reaction, A plus B goes to C plus D, or C plus D goes to A plus B. It's not that. An equilibrium constant or an equilibrium reaction means that they are occurring simultaneously at the same time. I think that's repetitive. They're occurring at the same time. So A plus B making C plus D and C plus D going back to A plus D, A plus B is occurring at the exact same time. Okay. It's just once forward and once reverse at the same rate reaction. Okay. That's the end of chapter 2. Now, in this particular PowerPoint, I've combined 3 and 4 together. So we've been talking for a good 20, 30 minutes now. Take a break. This is your time to kind of pause the video, come back to it, right? Because this is a YouTube video. You can always come back to this, pause, go outside, take a break, and then return. But if you're going to power through it, welcome back. And let's get forward. So now we understand the process of chemical reactions. We get atoms, we get chemistry. This is all review. Great. Now, why is water its own chapter in this textbook? The reason being is because water is so universal in our life. It is so important that not understanding water is probably going to do it a disservice. Our body's composed of 70% water. That's a lot of water. If you were to dehydrate a human body, we go from, I don't know, 150 pounds down to 20. Like, water is so much of us that it has to be in its own chapter. So at least that's the way I like to think about it. Anyways, now, because of this polar covalent interaction, back and forth, okay, when water slows down, cools down, okay, remember, the heating of water and the freezing of water, the only change is the amount of energy added or taken out of the system. Is it endergonic or exergonic? Sorry, I'm using the word endergonic, exergonic. That's in biology. That's what we use. Another way of saying endergonic or exergonic is endothermic, exothermic. Okay, they're exactly the same meaning, except one is for a living system. But in our case of water, if we're adding energy into the system, it's being endothermic, right? We're adding energy in. It's pulling heat away from my body into the water itself, and it will utilize it, and it will speed up the movement of the water molecules. And if we are taking heat away from the system, being exergonic, right, the water will eventually slow down, where it forms a solid. Okay, because we're removing energy away from the water molecule, taking energy away, sucking it out of it, and slowing it down. So it's very hard for students to kind of get that because they're thinking endothermic being cold, right? And cold as ice, that's not it. Okay. It's not a cold reaction where we're making ice. An endothermic reaction melts the ice. Okay. If you put ice in your hand, right, over time the ice will melt. The reason why it feels cold is because it's sucking the extra energy that your hand is producing into the ice cube, melting the water, speeding up the water molecule, melting it all over the floor. Exothermic, the reason why exothermic feels hot is because the water molecule is giving off the energy back into your hand. So if you put your hand over a boiling pot of water, right, it feels very, very hot. But over time, what happens? If you look underneath your hand, a lot of condensation occurs. That, because the water molecule is cooling down. It's slowing down, it's reforming back into a liquid. Now, for this particular slide, just know that if water cools down enough, if we pull enough energy away from water molecule where it becomes slow and stays in one spot, its positive negative behavior, its polar behavior, its hydrogen bondings that it can form with all the other water molecules is going to align itself into a perfect crystalline structure. Now, if we compare the two images, these two images are the same size. But one image has more water molecules than the other. It's more dense than the other. If you look at the structure over here, you can see less water molecule, more empty space. More empty space, less density. Less dense, ice floats. Okay? Hopefully that makes sense. Again, rewind and replay this again. We went through quite a bit just now. Okay? But ice being less dense allows water to float. And with the floating of water, right, we have life. Imagine if ice sank, right? Imagine if it became more dense and it sank. During wintertime, those lakes, those oceans will be a solid block of ice. No life can thrive in that environment. And that's just amazing. This single property of water allows a whole Arctic ecosystem to occur. And that's just amazing on its own. Anyways, let's keep going. So, polar covalent bonds, polar molecules, we already talked about that last chapter. I'm going to skip it. You still need to know it, but I'm not going to talk about it again. Now, four emergent properties of water, or four properties that occurs because of this water. We have a cohesive behavior, moderating of temperature, expansion on freezing, and being a universal solvent. Now, when we're talking about cohesion and to an extent adhesion, I want you guys to write this down. Cohesion is water interacting with water. They're cohesively interacting with each other. Co meaning is the same. They're cooperating. Okay? Adhesion, like adhesive, you put an adhesive, a tape onto a wall. Those are two different elements, two different compounds, right? So adhesion is water molecules interacting with something else. Cohesion is water interacting with itself, okay? And through cohesion, you'll have a web of water molecules because of the hydrogen bonding. Notice if we go back, you see this webbing of hydrogen bondings. Now, again, it's like a magnet. With this extra webbing here, you have a thing called surface tension. And that is the strength of that webbing, that water molecules holding on top of each other at the surface of, of the water level. Okay. Now, like with any webbing, if you think about a spider's web, if a little tiny fly was to hit a spider's web, can it break through if it's very small? No, right? Why is that? Because the fly itself didn't have enough force to break through the web. It was too weak. If a bumblebee or a praying mantis or some big bug was to go through that very same spider web, depending on how the size of the spider web, mind you. But in this example, let's keep it simple. It's a huge item. Let's say a tennis ball. Say that I got a tennis ball and I threw it at the spider's web. Will it go through? Most of the time, it will. Why is that? One, the tennis ball is huge. But mainly, two, the force that the tennis ball is exerting onto the spider's web is going to break through it. There's enough force, enough pressure to go through. So I want you to relay that visualization to surface tension with water. At the surface of the water, if I put a leaf on top of the water, most of the time it's going to float. Why is that? Because the force that the leaf is pressing onto the water cannot overcome the hydrogen bonding that the water molecules are cohesively doing to each other. But if I dropped a piece of rock onto the surface of the lake or the surface of the water, the rock is going to go straight through down to the bottom. Why? The force that the rock was able to exert overcame the cohesive resistance. So some insects have evolved and adapted so that they are able to distribute the force over a broad area and have the ability to walk on water, such as this water strider. Okay. Now, adhesion, again, I'm not going to talk too much about adhesion, but we're very familiar with it. Put a paper towel into a cup of water, what happens? The water, and you just put the tip of the paper towel into a cup of water, you can see the water climbing. That is adhesion in action. Now, for this, we have evapotranspiration. Now, evapotranspiration is something that we'll learn a little bit later down, more so when we're talking about plants. But just know that for water to travel up the stem, the trunk of a plant, say a redwood plant, it needs to have the ability to get water to move from the ground all the way to the top of the canopy of the tree. Canopy being the tip of the tree. Okay. Now imagine how much work, how much pressure you would need to be able to take water from ground level, below ground level, all the way up a couple hundred meters, 100 feet. That's how big a redwood tree is. Now, it does this through the properties of diffusion and osmosis, and to an extent, just physics, right? There's an area of high pressure versus area of low pressure. Again, we have high concentration and pressure of water at the bottom and low concentration and pressure at the top. Now, we'll soon learn the movements, the passive movement of molecules always goes from high to low. So in this case, it will freely move from the ground up. But the only way that we're able to have it move up is through that process of evaporation, where the sun is hitting the canopy, evaporating the water, causing an air of low pressure, then we're able to push it up. And the reason why water is able to climb up is through the process of adhesion. It's able to stick to the wall and climb. It's like you climbing a ladder. Every hand's on the step of the ladder with another one. That's adhesion in action for a water molecule. Okay. All right. So that's one. That's the properties of cohesion. Now, temperature. Okay. You guys know temperature is movement of molecules. That's all it is. It's kinetic movement. It's motion of molecules. And with the accumulation of this motion, this average of motion, this is what we call thermal energy, right? The movement of molecules hitting a receptacle, hitting a thermometer, right? We are able to read that. That is the overall thermal energy, aka the temperature that is registered. Okay. Again, thermal energy is more specific to the kinetic energy movement. Okay. But temperature is what we call it as the average of all the thermal energy in a given area. Now, for us, thermal energy is also what we call heat. That's what heat is, right? If you put your hand above a stove, you're going to feel the thermal energy. You're going to feel the heat of the fire, right? So that is what it is. Now, for our case, when we're talking about heat, we're not going to talk about joules. Yes, we can. Okay, but that's mainly chemistry, biochemistry and chemistry. For our sake, we generally talk about calories. Okay, now a calorie is essentially how much energy you need to raise 1 gram of water by 1 degree Celsius. Wait. Hold on. Let's take a step back. That sounds so familiar, doesn't it? That sounds like specific heat, which you are correct. Specific heat is the amount of energy required to raise 1 gram of water by 1 degree Celsius, or 1 gram of a substance by 1 degree Celsius. But because we're in biology, we're going to talk about calories, okay? And we're going to relate it to water itself. So every calorie that you see is always going to be compared to a unit related to water. Don't get too confused about that. Just take it at face value, okay? Now, a kilocalorie is what we are used to seeing on our nutrition label. If you look at the back of your protein bar, or if you look at the back of your snack or your food, your pasta, for instance, and you look at the description, calories is capitalized. Now, in nutrition, capital C, because we don't want to scare people who are purchasing food products from the company, we want to make it less intimidating. So instead of saying kilocalories, we replace it with a capital C and label that as calories. But just know, 1 calorie, 1 calorie, lowercase, is equivalent to 4.184 joules of energy. Wait a minute, 4.18 joules. That sounds like something that we have learned last year. Yes, it is. It is the specific heat of water. Remember, it's related to water. So 4.184 joules, we can replace that with calories. And everything else should be the same, grams per degree Celsius, right? That's it. So specific heat of water for biology is not 4.184 joules per grams per degree Celsius. That's for chemistry. For biology, it is 1 calorie. We want to make it easy for you guys. So we're going to say it's 1 calorie. That is your specific heat of water. 1 calorie per gram degree Celsius. That's it. So that's how much energy is required, or how many calories is required to raise a gram of water by a degree of in centigrade. All right. So when we give water enough energy, it's going to go from a liquid to a gas. Think of boiling pot of water, liquid to gas. Now, because water molecules are turning into steam, into evaporating gas, the hydrogen bond that holds the water together as a liquid is now being broken because the molecules are moving way too fast. It can't hold on to the water molecule. It's too energetically active. Think of a puppy, right? Super energetic, active. You can't contain that puppy. It's going to start running around. That is water with excessive amounts of energy. And vice versa, if we release all that energy, use up all the energy, it's gone, it gets tired, it slows down, and hydrogen bonds take over and reform. Okay? So, specific heat, aka calories, is involved indirectly with that description. Now, why is it that this is important? Because coastal areas, if you've ever been near the coast, which we all are, we're here at Long Beach currently, temperature doesn't fluctuate too bad. It's generally in the same vicinity throughout, give or take some exceptions. Okay. But if we go to the Inland Empire where it's much drier, drive down the 91, yeah, go back in. What you're going to find is that the temperatures fluctuate quite drastically. In the evening, it's icy cold, and in the daytime, it is blistering hot. There is no stability. And why is that? Because there is no water in the environment, in the air, to kind of absorb the energy or release the energy at a constant rate. Versus near the ocean, at night, it might be 68 degrees Fahrenheit, and in the afternoon, it might be 75 degrees Fahrenheit. Very little fluctuation. Okay? Because all the water molecule is absorbing and releasing that energy. So here's an image that we can see. Okay? Now, heat of vaporization and evaporative cooling. Heat of vaporization is going from liquid to gas. How much energy is required to change the state, and evaporative cooling is the exact opposite from gas to liquid. Okay. Solution, solvent, solute. I'm not going to go too much over that. Solvent, water, liquid, right? Dissolving agent, if you want to think about it that way. Solute is what we dissolve the stuff in, the solvent with. Okay. Solute goes into solvent to make a solution. An aqueous solution is the one where water is the solvent. Okay. So this is sodium chloride. Okay. Hydration shell is being built. Notice all the oxygens right here, the one in red is negatively charged, and it is surrounding the positive sodium. And vice versa, all the hydrogens, H plus areas, okay, it's not hydrogen ions, it is partially positive hydrogen, right? So we need to include the partially positive areas, is surrounding the negative chlorine ion. And because they're crowding around, they're stripping away sodium from chlorine. And you do this enough, you create a solution. So these hydration shells are important. Okay. And they're going to be very important later on when we talk about the movement of protein, the holding of protein in a tertiary state, so on and so forth. Okay. Now, hydrophilic versus hydrophobic interactions. Hydrophilic, water-loving, hydrophobic, water-fearing. These are terms that you guys should be familiar with, but just know that polar molecules are hydrophilic. They love to interact with water. Hydrophobic molecules, such as fats, will not interact with water very well. Think of oil and vinegar or oil and water. They have two distinct layers. They won't interact as easily. Okay. And that's the end for chapter 3. Now, I'm going to go just a little bit more. Bear with me. This is one big, massive video, but we have 3 chapters that we're going over. Okay. We should have, I don't know how many slides left. I really don't know. But take a moment. Okay. Let me see here. Yeah, we're going to keep going. Okay. All right. So chapter 4, carbon. Now you guys know about how chemistry is applied to water. Now we're going to learn more about how chemistry is applied to carbon. Okay. Now, with this, be familiar with the forms. Be familiar with the Lewis structure, with the carbon skeleton structure, the ball and stick model. You got to get familiar with it. But mainly, what you guys need to get familiar with is the functional groups, your OH groups, your COOH, your NH2s. Those are properties that you guys need to kind of recall. And this here is the beginning of your organic chemistry understanding. It's really this simple fundamental that is built into your organic chemistry classes later on. Okay. But we're not an OChem class. You will need to know some OChem concept because it overlaps with bio, unfortunate or fortunate. Okay. But we are not going to be mainly focusing on reactions. We are focusing on the application of the reactions involved in a cellular setting. Okay. So we're very familiar with hydrogen, oxygen, nitrogen, sulfur, phosphorus. Okay. Now, these are all required for life, okay, in biology. And the reason why carbon is such a nice element is because it can form 4 bonds. It has 4 unpaired valence electrons. So it can form 4 bonds, which gives it a lot of flexibility when creating different structures. Now, this is an example of methane, ethane, ethene, prefixes, suffixes. You guys will need to know that in organic chemistry. You may need to know a little bit about it in biology, okay? But I'm not going to ask you, what is N-butyl, tetrahydride thing. I'm not going to do anything like that. But what I will expect you to know is, what is ethane? What's methane? What does it look like? Right? Those are things that are fair game. Something simple. I'm not going to ask you for IUPAC naming. Don't worry about that. But just know the basics. Okay? So CH4 is a methane molecule. Structural formula, Lewis structure. Those are prereqs that you should already know. Now get familiar that because of this flexibility, we can create many, many different types of molecules. Here's an example of a steroid molecule or a lipid molecule. Okay. Lipids being the general classification for fats, hormones, and cholesterol. Okay. So this is two examples, very similar in shape, but different in molecular makeup. Okay. Carbon skeletons can vary in size and shape. You can have double bonds throughout. You can have isomers. You can have rings. You can have T shapes. There's a lot of things that we can do with this. And for most part, it's made out of hydrocarbons, hydrogen and carbon atoms. Okay. All organic molecules will have hydrogen and carbon atoms. Fats, a lot of hydrocarbons. Okay. So just be wary. Even our amino acids have a lot of hydrocarbons within them. They're basically the backbone. So, but right here is an example of it. We have fat molecules. We have adipose tissue. This is an example of human adipose tissue. You can see the nucleus, you can see the fat droplets. Okay. And within the fat droplets, we have these triglycerides. So isomers. Get familiar with the term iso and the term mer. Iso with the suffix mer. Mer just represents unit. And why this is important in chapter 5, we'll talk about polymers and monomers. But mer just represents the Latin suffix for unit. Iso representing the same. So when we're combining the two terms to get isomer, we're talking about the same unit. Now, that doesn't make much sense, but if we break it down even further into chemistry terms, same unit means same molecular formula, different way of creating the structure. Okay, same formula, different structure. So you can have structural isomers. Now, these are just rearrangement of atoms that uses the exact same pieces, but just built in a different way. Cis and trans isomer will require a double bond present, but you either have it on the same side or alternating sides. If it's cis, it's same, trans is alternating. And enantiomers are mirror images of each other. Okay, so here are just examples, and I'm hoping this makes sense. Again, cis means that you have groups that are protruding on the same side, and the other sides are generally going to be hydrogens. So if we divide this molecule up in half, you can see one side is hydrogen, the other side is the X molecule. And on this end, if we try to do the same thing, it's alternating and opposite. So it's in a diagonal form. Okay. So again, review over these three terms and be familiar with the structures. If I was to show you two structures, can you label it as enantiomers, isomers, etc.? Okay, what type? Now, why is this important? Again, remember what I told you guys earlier this PowerPoint. Specificity, shape is important for the tools of our body. If you don't have the right shape or the right fit, it's not going to work. So right here, we have two compounds. You have S-ibuprofen and you have R-albuterol. Now, these are active ingredients in Advil and decongestion medicine. It opens your bronchial pathways if you're talking about albuterol. Okay. And this is what doctors will prescribe to newborns or to people who have breathing issues when they have a cold or flu. Albuterol. You use an inhaler or a respirator or a nebulizer. All right. Now, if we gave patients the enantiomers of that, where it's R-ibuprofen, mirror image, and S-albuterol, mirror image, it will not work, even though it's near identical in shape and structure. But because it's mirror image of each other, it will not bind to the receptors within our body, and it does not work. Our bodies can't recognize it because it's not what occurs naturally. So just be careful with that. Okay. Anyways, these you guys can read on your own. I highly encourage just reading these bullet points every so often. Okay, but I do want to get the big, big points down. Functional groups. Oh, this is a big one. This is huge, 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 huge. Understand your functional groups, what's polar, what's non-polar, and what be able to recognize them. You have hydroxyl, OH, alcohol groups. That is probably the most important that you'll ever see in organic chemistry, biology, etc. is OH groups. Those are such nice groups to identify. Next, you have your carbonyl, your C double bond O. That should be self-explanatory. Now, if we combine carbonyl with a hydroxyl, we want to combine the names, right? Hydroxyl, carbonyl. If I combine it, carboxyl. Get it? Carbonyl, carbo, hydroxyl, carboxyl. So COOH, if they're together, is what we call a carboxyl group, where we can form carboxylic acid. Okay. Next, amino group, NH2. You might see NH, which is amide, but we're not going to deal with amide too often in this class. Sulfhydryl group is sulfur with hydrogen. Phosphate group, PO4. And methyl, ethyl, propyl, those are just carbon chain with one hydrogen missing. Okay. Last but not least, I think this is the last slide, and then we're done. Notice the name, adenosine triphosphate, ATP. Now, you guys are going to be very familiar with this molecule by the end of this semester. You're going to have ATP, ADP, AMP, cyclic AMP. You're going to know all of that. But the only difference, chemically speaking, the only difference between ATP, ADP, AMP, and cyclic AMP is how many phosphate groups are there and how is it connected. That's it. ATP is what is shown. You have 3 phosphate groups attached to an adenosine base, a nitrogen base. ADP, all we're doing is removing one PO3, one phosphate group. We just remove it. AMP is 2 phosphate group removed. So this is how our body utilizes energy. Remember, energy, what is energy? Energy is movement. It's like electricity. If we really want to keep it simple, it's like electricity for our body. Where is the electricity found? Right here in the phosphate group, phosphate bond. Right? There's a lot of energy stored within the bond because it's holding 2 highly, highly electronegative atoms together. Right? Phosphate, well, phosphorus is not super electronegative, but it's holding them together. And as it holds, if you're able to break it and release it, a lot of energy is going to get released. Okay? So that's it. I hope this video was good for you guys. This is chapters 2, 3, and 4. Now, I will try to make more videos. I can't promise you that I will be able to do it for every single chapter, at least at the time of this recording. For you guys in the future, we might already have the videos, but at least at the time of this recording, I cannot promise that I can get everything done in every time. Okay. So in the event that I'm able to, great. In the event that you guys are doing this in the future after I've finished recording, great. But for you guys currently watching this live, or at least during the time, I'll try my best. But until our next video, if you have any questions, let me know at the end of class or during class, or visit me in my office hours. Okay, that's it for this video. Take care, everyone, and stay tuned for chapter 5.